Okay, let's get started. I'd like to remind everybody if you can put your cell phones to silent mode, that'd be much appreciated. Anyway, good afternoon. My name is Adam Noonchester, and I was an AI programmer on Sunset Overdrive for the full 3-year development cycle. I've worked on most of the normal enemies in Sunset Overdrive, and I'd like to take this opportunity to tell you about some of the problems that we had to solve. So this is Sunset Overdrive, and at its core, it's an open-world, third-person shooter that places a heavy emphasis on player agility. We wanted the player to be able to combine moves like air dashing, bouncing, wall running with things like grinding on objects, and we wanted the players to be able to combine those with crazy weapons like a propane tank-powered rocket launcher and a gun that shoots ricocheting vinyl records to be able to stylishly kill humans, mutants, and robots. In order for all of this to work, our enemies needed to do 2 main things. The first was that they actually needed to force the player to traverse. We had found very early on in our playtesting that if we didn't get players to start engaging with our traversal system from the very beginning of the game, then most players would try and play the game as if it was a normal third-person shooter, staying on the ground and stepping into and out of cover. Therefore, our enemies needed to be so dangerous and overwhelming that most players felt like traversal was required to survive. The second big thing our enemies needed to do was once players are actually up and traversing, the enemies need to test the player's ability to both shoot, traverse, and improvise at the same time. The idea is to encourage the player to play the game in a fun and stylish manner, because, well, technically, bouncing up and down on the same car over and over is using our traversal system. It's boring and not much fun. Another way to put this would be most players will try and play the game in an efficient manner. And we need enemies that will push the player to keep moving, improvising, and having fun instead of just trying to find exploits in our system. I'd like to briefly list some of the key ways that Sunset Overdrive is different from a more traditional linear shooter like the game I just worked on, Resistance 3. This game was a controlled experience. So not only did we know where the player would enter and exit each setup, but most setups were only used once, and so we could do a lot of custom tailoring to the environment. For example, we could build geometry that specifically matches our characters' sizes or even their capabilities. We could also limit options that we found were too easily exploited by the enemies or the player. Sunset Overdrive, on the other hand, takes place in an open world in which the player can approach most setups from many different angles. And AI will need to be able to cope with both this and a wide variety of spaces and metrics, and they're going to need to play well in spaces that were not specifically designed for them or even for combat in general. Another big difference between Resistance 3 and Sunset Overdrive is that in Resistance 3, both the player and the enemies traverse the same space in mostly the same way. They'd run around on the ground, and they'd occasionally jump. Wherever the player tried to go and hide, enemies could usually get there, and almost always by taking the exact same route the player did. In Sunset Overdrive, the player can bounce on cars, grind on power wires, and do many other things that enemies can't. We chose to do this to make the player feel powerful. However, this does mean that one of our biggest challenges is going to be creating enemies that can handle both this speed and maneuverability. Let's start with our most common enemy and the foundation to a large portion of our combat. We call this guy the base OD. His primary job is to force the player onto traversal. We'll primarily rely on other enemy classes to challenge the player while they are actually traversing. The base OD attacks by lunging at the player once they get within about 10 meters of the player. So while they've got a bit more range than a normal melee enemy, they're still going to need to be able to get pretty close to the player, and therefore they're going to need to keep up with the player. I'm not really going to focus on a lot of the normal things you do to make an enemy like this fun to fight, things like hit reacts, death, animation variation, effects, and how you tune a lunge. Instead, I'm going to focus a lot on the things that we needed to do in order to get a melee character able to keep pace and challenge a player that is as highly mobile as the one that we had in Sunset Overdrive. Here, we've got a fairly typical shot of Sunset City. And this is the debug draw for our navigation mesh, or nav mesh, or nav for short. This represents where enemies can go. One big problem is that there isn't nav mesh on any of the traversal elements in this scene. For example, this rail, wire, umbrella, or car. A similarly big problem is that by simply using a bouncy, that is an object that you can bounce on, such as a car or umbrella, the player can move from one section of nav mesh to a completely new section of nav mesh. If this happens, then the OD might have to run around behind the building and take the stairs to chase the player, or worse, they might not even be able to chase the player at all. If this happens, then the player will be free to just jump on top of the building and shoot into the horde without ever needing to traverse, and suddenly we had a very, very boring game. In Resistance 3, we had developed a concept that we called nav clues. We often refer to invisible gameplay markup as clues. Nav clues are basically two positions, usually annotated by designers, on nav mesh that we say are connected by a specific animation or action. So in this example, the two green arrows on the left side are connected by a 2-meter climb over animation. In Resistance 3, the majority of nav clues were in fact cinematics that would be played back exactly as they were animated in Maya. So in this case, the enemy would play his specific climb over 2-meter animation using the orientation and position of the starting clue as if it was the origin in Maya. This looks really great, but it isn't very flexible at all, and a lot of spaces in Resistance 3 had to be specifically designed to very strict metrics in order for this to work. If we want to cover this city in nav clues that allow our enemies to navigate the world, then we're going to have trouble if we try and make custom animations to allow every character to climb over every single object. In just this one shot, we've got cars of varying sizes, we've got lots of different grindable objects, we've got planters, we've got all kinds of climb up and downs of both varying heights, with and without rails. And here's the nav mesh with the nav clue connections in the shipping game drawn in purple. Trying to make unique clips for every one of these shapes, for every single enemy class with a unique skeleton, and we've got more than a dozen of those, isn't going to be feasible. We also don't want to restrict art and design too much because that will make our city boring to look at and explore. So the first thing we needed to do was find a way to make our traversal system flexible enough for enemies to be able to get everywhere that the player can. We worked with our animators to divide each maneuver into parts so that we could hopefully mix and match them. For example, to climb over a rail like this, you'd play a climb up and then a climb down. Up, down. Two separate animations that we stitched together at runtime. To climb over this box, on the other hand, we could use 3 clips. Climb up, climb over, climb down. If the animators make a variety of clips that each begin and end in exactly the same pose, then we should be able to string them together to climb over all sorts of things, such as this box leading to a drop-down. Conceptually, this is the same as the previous box, because the character just climbs up and then over and then down. If the start and end position, or the start and end poses of each animation clip match, then we can substitute a different clip for any of the 3 parts without needing to change the other 2. This is how we're going to mix and match and be able to climb over a lot more objects with a lot fewer clips. We broke our traversal maneuvers up into 5 categories. Here in A, you can see the previous climb over. In B, we have the vault that I showed you previously. In C, we have a climb down, and in D, we have a climb up. You can see that in addition to the 2 green arrows, there's a third volume. Volumes are non-rendering cuboids that can be placed in our editor, and we oftentimes use them to define the boundaries of spaces or detect when the player has entered an area. In this case, we're going to use the size and placement of the volume to determine which of the maneuvers we're going to be doing. From the volume's width, we know how wide the thing that we're climbing over is, so we know whether or not we're doing an A, a climb over, or B, C, or D. From the volume's height relative to the start and end point, we know how far we're going to climb up and how far we're going to have to climb down, which will tell us the difference between B, C, or D. In fact, as the character is climbing up and over A, we guarantee that the first clip will scale to end with the character's root exactly at the height of the volume's center, exactly touching the volume's front face like this. Similarly, we scale the over clip to end at the back face of the volume. The last clip of the climb is scaled so that it's guaranteed to land on the ground, but its motion parallel to the ground isn't in any way restricted. So while some characters might land here, other characters might land here. The point of all this is that if the volume is properly sized and placed on the object that the character is going to be climbing over, then we're going to have great position, or precision, and it will look like the character is actually making contact with the environment. We do similar such scaling for B, C, and D. There's one other neat thing about our implementation. In our engine, our characters never directly play animation clips. Instead, they activate what are called animation drivers. These are data-defined blend trees, complete with parameters that can be set from code. On this side, you can see a bunch of orange nodes, and these are the actual animation clips. These clips all go into a blend node in the middle. This blend node is configured to select an individual clip instead of the default of blending two clips together. That blend node is set up to use a variable called height to drive which of the 7 clips is actually selected. So the output from this driver will be the clip that best matches the height that the character will actually be climbing. And what's great about this is that it allows code to operate without having any knowledge of what specific heights a character actually has. We just set a parameter in code, activate a driver, and then we scale the motion on whatever comes back. Because each of our clips is mostly linear in motion, since we're dividing each vault up into a sequence of parts, it's easy to scale the clips to have them end precisely where we said we want them to. If things look odd because we're scaling a clip a little bit too far, our animators can come back in and add clips as necessary without programmers needing to do any work. So I mentioned before there are 5 kinds of maneuvers. Well, the remaining one is jumping, and it really isn't that different from the others. We still break it up into 3 parts, a takeoff, an in-air, and a land, and we then set various variables about the characteristics of the jump, such as the vertical or horizontal distance, the character's foot state, whether or not his left or right foot is forward, that is, the character's speed, and then we activate drivers and work with whatever comes back. The big difference with jumps is that we determine the length of time the character is actually going to be in the air in advance, and then timescale that in-air clip to last exactly that long. This way, we guarantee that the character will have a consistent flight speed over all jumps, and that his feet will also touch down on the ground on the exact frame that the character's feet touch the ground on the final frame of the in-air animation. Here's an example of a takeoff driver for use in a jump. In this case, our output comes from a blend node that's governed by a speed variable. We're blending 2 clips, as well as the results of another blend node. That blend node will select between one of 2 clips, and that is based on if the character's left or right foot is forward. Essentially, without a programmer needing to do anything, we've set this up, someone has set this up so that we'll play a unique animation if the character is standing still, if the character is barely moving, or in the case that the character is running, he'll play a clip that best matches whether or not his left or right foot is forward. Here's an example of selecting between different in-air clips based on the distance we're actually jumping. So with this, our AI can now traverse all over this world and get wherever we want them to go. So now our next problem was, where do we actually want them to go? Remember that we have a very agile player that leaves nav mesh whenever they are using traversal objects. We initially started by just sending the base OD to the closest point on nav mesh to the player, but this has a number of problems. The first is that the closest point on nav could be on a bridge that happens to be above you. It could be on a roof that you happen to be just going by. Or if you're bouncing up on top of a car, it could easily move from the left side of the car to the right or from the front to the back. Now, in order to solve this problem and a lot of the other base OD problems I'm going to talk about, there's a little bit of a shift in our thinking that needed to happen. Because up until now, we've been thinking of each base OD at kind of the individual behavior level. Each guy would try to figure out what's the best spot for me to go to. The problem with this is that the best spot changes very quickly and is incredibly hard to predict with any accuracy. And so the consequence of this is that if all the base OD are trying to predict the same perfect spot, then they will all make the same dumb mistake when our prediction is wrong and the player does something unexpected. What we want is for somebody to frequently be in a good position. And the easiest way for us to do that is to use our high enemy count to try and calculate lots of interesting positions. To put it another way, we want to calculate lots of interesting places to be, paths to take to get there, and things to do for all the base OD instead of just having each guy do his own thing. So with that in mind, we developed something that we call the Nav Position Tracker. This will simultaneously track several different kinds of positions shown here by debug spheres. We track the actual closest point on nav to the player. We track the closest point on the ground to the player's ground, the closest point on nav to the player's ground position, as well as the closest point on nav to positions slightly offset from the player's left, right, forward, and back. Now, the way this actually works is that each base OD picks the position that is currently closest to him and then goes there. Since the base OD should be spread out, this means that we'll have different base OD trying to get to different spots. Without the position tracker, you'd wind up with base OD just orbiting the car as the closest point on nav jumped from to the left or the right or the front to the back. But we don't have that problem now because we've always got positions on the different sides of the car. In this case, without the position tracker, what would happen is the closest point would be on one side of the rail, and then when the player switches directions, it would jump to the other side of the rail. This would cause the base OD to think they need to jump over the rail or run around it in order to keep chasing the player. Now, since there are always positions to the player's left and right, we don't have that problem. And here you can see that as I grind around, there's always a position on the ground below me. Other positions occasionally jump up to rooftops as I skate by, but what this allows is for base OD who are on the ground directly below me to continue chasing me from there. But others who may be a little bit farther away or a little bit higher may decide to go to the top of buildings that I'm moving by. And this is great in case I decide to get off there, because there'll be an enemy waiting for me. So here, we now had enemies that could chase the player, but it wasn't enough. As you can see, they tend to clump up, or in other cases, they'll conga line once they've been chasing the player for a little while. We need to get the base OD to spread out. This will make the game feel more dynamic, more challenging, and hopefully it will make our enemies seem more lethal and thus capable and intelligent. Well, we started trying to solve this problem by using an old Ratchet and Clank technique called arc angles. An enemy approaching the player with an arc angle of 0 will run straight at him, while one approaching with an arc angle of theta will kind of take the top path. Negative theta is the bottom path. All of these arc angles are managed by a flanking manager that exists on the hero, or the player. It assigns out angles to approach at so that we don't have all of the base OD approaching from the same direction. This actually works pretty well when we're near the player. Here's that same mob of base OD using arc angles. They do a much better job of spreading out, and I have to work much harder to avoid being hit. At a low level, arc angles work by changing the position an AI is actually trying to nav to. So as the base OD or the player moves, we recalculate a position along the arc angle path and try and go there. In order to prevent arc angles from sending guys to the wrong side of walls, we require that the line from the target to the arc angle position to be unobstructed on nav mesh. In practice, this means that because our world is not a flat, empty plane, the arc angle destination will usually be within 5 to 10 meters of the player. This has the unfortunate effect that if a group of enemies is far away from the player, then there's a high chance that only the final leg of their path will significantly vary, and we want them to spread out from the beginning. So we're going to need other solutions for getting base OD to spread out when they're far from their target. Our first idea was, hey, let's go in and make all of the polys involved in a nav path more expensive so that subsequent nav path queries by other characters are going to be more likely to find an alternate path. This didn't work. As you can see, the shape of nav polys doesn't necessarily correspond to features in the world. Here, there's just a bunch of polys coming together in the middle of a street. Here, we've got a thin sliver of a triangle that's sandwiched between two large triangles. And this inconsistency in the nav mesh can cause strange things to happen. For example, say we have a character move along this path. This would add cost to these polys. That's not going to have much effect on a path starting at a nearby position, which isn't particularly great. However, if we move both of these path endpoints down a little bit, then, well, this becomes the lowest cost path, which is even worse. What we needed was to add cost to places, to important places, in ways that don't have awkward knock-on effects. The other problem that we had with adding cost to individual nav mesh triangles was how are we going to efficiently store, utilize, or access this data when there are multiple base OD trying to go after multiple targets. We've got an 8-player multiplayer mode, as well as some big multi-faction fights. Instead of that, the first thing we did was go in and add cost to individual nav clues. Here, you'll see a bunch of characters trying to get from one side of the fence to the other. You'll see purple lines begin to stack up as nav clues change their cost. As you've seen in some previous slides, our world's incredibly dense with nav clues, so that makes adding cost to them meaningful. Additionally, since they correspond to actual visible geometry and are typically very close to the nav mesh boundaries, they don't have the same awkward problems that adding cost to polys does. Seeing one character jump over a car while another one runs around it doesn't look odd at all. Basically, if a bot gets a path that goes through a clue, he'll increase the cost of using that clue so that subsequent path queries will be more likely to find another path. As an additional layer, bots who get close to a clue that is already in use will immediately try and find an alternate path. And this is what causes the cost to go up and down in this video. Adding cost to nav clues combined with arc angles still wasn't enough, since a bot could sometimes get a path that went for a really long distance without going through any nav clues. Enter what we called influence spheres. Our engine group gave us this ability, and we can basically bundle a collection of spheres and associated costs along with a path query. In the above screenshot, there are 4 such spheres drawn in red, such as this one in the bottom left. And basically, it makes crossing that area more expensive, but only for that path query. And so the way we utilize this is that when a base OD does actually ask for a path, which is fairly frequently, he'll talk to the aforementioned flanking manager, the guy handing out all the arc angles. It will then examine all of the paths that all of the base OD chasing this target are using and look for common and close bend points. It will look for these bend points and make sure that they're not too close to the base OD or to his target, and then place influence spheres on top of them to try and force the guy to find an alternate route. Now, this works fairly well because path bend points correspond to features of the geometry. Otherwise, there wouldn't be a bend point there after we had run path smoothing on it. We keep the size of the influence spheres relatively small so that they don't result in if they don't result in a substantially different path, smoothing will just be able to iron out any differences. And this prevents the base OD from looking like they're just running around objects that are invisible and don't exist. So up to this point, we've done a lot to the base OD to make them dangerous and thus fun when the player is close to the ground. They spread out, they surround you, and they tend to kill you if you aren't playing well, and this really encourages a lot of our core gameplay. However, if you get up high, it's trivially easy to grind back and forth and just kill all of them without any resistance. I mean, base OD are supposed to be vulnerable to traversal, but right now, it's so dominant that the player no longer needs to put any thought or effort into playing once he gets about 3 to 5 meters off the ground. And things quickly get boring because of that. Our last goal with the base OD was to occasionally get them to be a threat to the player even when he's traversing. This wasn't something we wanted to have happen often. It's just something that needs to keep the player from going into autopilot. Our desired solution was to try and get the base OD perched up on individual traversal pieces that we think the player might use. If the player gets too close, the base OD will try and hit them. In order to figure out what traversal to use, we collect all traversal near the player and rate them on a few factors. The first is that every time the player uses a given piece of traversal, we make it tastier. This is very important because what we really want is to encourage the player to keep moving forward. We don't want them to stop and use the same little piece of a grind wire or the same bouncy over and over again. The second thing we do is predict where the player will be in the next second and make the traversal in that area more attractive. The third thing we do is factor in how close each individual base OD is to each piece of traversal. Here you'll see as I traverse up onto wires, a bunch of boxes will appear. These are potential places for base OD to wait for me. Lines going down to the ground correspond to jump up positions that we validate with raycasts and nav tests at runtime. Base OD can wait on either bouncies, hang or grind hang or perch on grinds. And then we restrict them so that no more than 25% of them can be waiting on traversal at any one time. It's also worth mentioning that we turn on this functionality gradually along with some other base OD abilities over the course of the campaign. At the beginning of the game, they never wait on traversal because we're trying to convince the player to use it as much as possible. Let's put it all together really quick and take a look at an encounter with a group of base OD much later in the game. One thing you should be able to notice is that they immediately start spreading out. They're also immediately starting to get up on pieces of traversal, and I'm about to get hit by one of them here. You'll see a guy using a jump to get over a car. You'll be able to see characters using volts to get over the trucks. And you can see how arc angles and influence spheres and all the things that we've talked about keeps the mob spread out. And I have to keep working in order to stay ahead of them. I can't just sit on the ground and wait for them to come to me. So you'll notice here as I get up on this roof that I'm going to get down off the roof, and then you'll see all of the base OD take different nav clues in order to chase me down to the ground, which will illustrate how our clue weighting helps keep them spread apart right up here near the top. Another interesting thing to notice is that I'm starting to fight back now, and even though base OD are pretty fragile and tend to die pretty quick, that around here I've taken out about a third to half of them, but they still do a pretty good job of staying on me. Here I try and just sit on the ground for a little bit, and there's almost immediately a guy there to say, hey, you need to keep moving, you need to react. This is an action game, not one where we want you to just sit on the ground and shoot. Another great side effect that we had once we had enemies that were this capable was there isn't a need to spend a significant amount of time hunting down that one last guy at the end of the setup. Most of our setups tend to end pretty gracefully. Let's move on to some of the main problems that we had with ranged enemies. Now, these are our three main ranged classes. The guy on the left is called the Blower. He attacks by lobbing green projectiles at his target. In the center, we have the Physco Rifle Bot. He attacks by using a plasma rifle that fires large, high-damage, but slow-moving shots. On the right, we have the Scab Shooter. He's basically a post-apocalyptic jerk with an AK. The biggest thing with ranged enemies is where they choose to fight from. We could, of course, just have them follow the player and shoot, but that typically overwhelms the player really quickly and makes the enemies feel like cheap and dumb versions of the melee class. What we really want is for them to go to interesting positions and try to engage the player from there. In all our previous games, this was done with fire points. These are fixed positions marked as being suitable to shoot from. Usually they'll be suitable for taking cover at and have a direction associated with them. Here you can see an example of common fire point markup in our editor. The selected fire point could be used to roll out to either the left or right to engage a target. And during combat, bots will gather all nearby fire points and score them on some criteria like proximity or line of sight. We actually started using both fire points and cover with all of our enemies in Sunset Overdrive and ran into several problems related to both the speed of traversal as well as the game's open nature. Getting into and out of cover is slow. This made our enemies feel really unresponsive and dumb as the player would flank them and they'd take too long to get out of cover. It also felt unfair to some players that enemies could take cover behind objects that they could not. Proper cover usage is also heavily angle dependent. You don't want to use a piece of cover that will point your back at an enemy. And given how fast our player moves, what fire points are valid wound up changing really quickly. We actually tried to continue to make this work for a while. We added a lot more fire points. We even went so far as to put fire points on a 1-meter grid in the world to give characters enough options to compensate for these rapidly changing angles. But this only made things worse because it could cause a group of enemies to bunch up with guys using lots of nearby fire points, or a single character might kind of dither between two adjacent fire points. And then By this time, trying to compensate for this heavy distribution of fire points along with a rapidly moving player was causing our scoring functions to go completely out of control, where we're trying to tune a formula that would take into account the angle of the fire point, how much cover does it provide, how much line of sight does it provide, is it close to, is our friends too close, are all the enemies too close, is it near our ideal range, is it near our combat anchor, that is the place the designer wants us to fight from. How dangerous do we think it is? Is it too close to where we are right now, or is it too far from where we are right now? Now, this is a very complex function that had become very noisy, and this noise manifested itself as inconsistent behavior, which was really bad because the AI would seem to react randomly. And this often led to them being perceived as either being stupid or unfair based on what that randomness was. We came up with two alternative solutions. The first one was what we call perches. These are elevated positions that bots can take and then jump between. We'd use them on long legs and resistance, and despite being fairly similar to fire points, they offer some big benefits in Sunset Overdrive. They're omnidirectional, which makes evaluating them a lot simpler. The second is that in a given space, there really aren't that many objects that are suitable for perching on, and this makes our scoring a little bit simpler. The third thing is that they separate the character from the ground and cause them to be silhouetted against the sky. This was incredibly important for the blowers because they tended to get lost in the crowd when they were at the same height as all of the rest of the crowd or horde of base OD. The final advantage is that jumping between them not only looks cool, but when we do it in response to being shot by the player, it's almost as effective as taking cover. That said, we still wanted our enemies to be able to use the environment to shield themselves. This would add more variety to our enemies, encourage the player to move around, and hopefully add a different kind of rhythm to combat to make human enemies feel and act a little bit more natural. Around this time, we were focusing on the layout of simple combat spaces that the player could approach from multiple directions. Our inspiration was a scenario similar to this slide. If you can imagine that this is a top-down view of a space, and the circles correspond to trees or pillars. Our basic idea was that the player might be fighting some enemies in this mix of tall occluders. As the player, you could move slightly to the left or right to fall into the shadow of one of these objects and take cover. Now, in our fire point-based solution, we'd place 4 or 8 points around each of these to allow our bots to choose between them. So now our world looks like this, or this to the AI. And hopefully, you can see why our scoring functions might start having trouble deciding on a consistent best location. It gets even worse when we start trying to find positions for multiple bots because they may all grab fire points that are close to each other. Our solution was to stop pointing out places to stand and instead point out objects to use and dynamically figure out where to stand to fight our current target. Imagine that the green circle is our target, and we want to use either the circle or the square-shaped object to attack them. If we draw tangent lines from the target to our box and the circle, you can see that those lines define a gray occluded area. We can easily calculate the tangent positions and vectors, and using these, we can construct everything else we're going to need. If we move back from the tangent position and rotate inwards, we can easily calculate a spot that's just inside the occluded space and thus hidden. Similarly, if we rotate outwards, we can calculate a good spot that's just barely visible to fire from. We've now got 2 points that we can step between that allow us to move from occluded to not occluded and mimic cover behavior. As the green circle, that is our target, moves, we can easily recalculate the tangent lines to get new in-cover and out-of-cover positions. We can also perform any kind of raycasts or nav checks between any or all of these positions at runtime to make things more robust. Here's a video of a scab using some of these occluders. You can see him step out to fire at the player and then reposition to use a different piece of occlusion. In Sunset Overdrive, we force our AI to change occlusion and markup on a regular basis to keep things active. I'm going to turn on the debug display here, and you're going to see some red and green lines. These are raycasts that we do to verify whether or not we can see our target from the out-of-cover position. Each of these large objects in this scene is a single piece of occlusion, and since there are much fewer of them than there would be with a fire point-based solution, and they're on actual features of the geometry, we don't need strange scoring factors in order to keep guys from bunching up. Additionally, as I move around here, you can see that the positions get dynamically recalculated. Because of this, we don't need to consider angle when deciding what piece of occlusion to actually use. In fact, our scoring functions really only needed to consider three things: line of sight, distance to the target, and the proximity to where the designer wants our squad to be, something we call a combat area or anchor. These are, in fact, the exact same three things that our perch scoring cares about. This kind of occlusion actually works well for fighting a target that is on your level or above you. However, when your target is below you, oftentimes the ground below you prevents you from firing. Moving down to your target's level isn't always desirable from a design point of view, so we needed a way to get enemies to use the edges of buildings as cover. Our concept is mostly the same. This is a side view, and we want to use the front-facing edge of this building to attack our target. A tangent line from our target through the building edge defines our occluded area. If we take our height into consideration, we can find a place to stand. Stepping forward from there will give us a place to shoot from, and we've got our two positions to move in between. In practice, this is what it looks like to the player. The enemy steps forward and is now able to shoot at the player. He's then able to reposition and step back to become occluded again. We call this line occlusion because it's generated in the city by marked up lines that the player uses to know where he can grind or pull himself up onto buildings. Here's a view from above. The blue spheres are the tangent positions. The yellow are the out-of-cover positions, and the red are the in-cover positions. Our bots will only begin looking for this kind of occlusion once they determine that normal box and cylinder occlusion will not allow them to fire at their target. So now we've got ranged enemies that can move between interesting places in the world and fight versus our highly mobile hero. However, we started getting a lot of feedback around this time about the game feeling too chaotic, unfair, and frustrating, particularly when ranged enemies were involved. The core problem was that it wasn't clear to the player what the enemies were doing and what the player should do to avoid being hit. We were asking the player to continuously traverse, and it felt like we were punishing them for doing just that. Players would frequently find themselves in situations with blowers, scab shooters, or physical rifle bots where there were just bullets everywhere at seemingly random times, and they had no idea what to do. It was even worse when traversing. We didn't want players to feel like they had to fall back on cover-based shooting mechanics, and so we needed to start challenging instead of punishing players who were actively traversing. We started trying to address the blower problem the same way that we address every mortar-based enemy attack, by adding reticles to the ground. Unfortunately, there were often so many reticles, and they would appear so randomly that players still didn't have a clear idea what they should be doing. We tried reducing the amount the blowers fired, or prohibiting them from firing if there were already too many shots in the air. But this made the blowers feel impotent and dumb because they could wind up on screen aiming directly at you and not be allowed to fire until a couple shots hit the ground. This also had a negative knock-on effect on difficulty, since increasing the enemy count beyond a certain point no longer increased the difficulty. What we decided to do was manage all blower shots versus a single target as a group. The idea was that individual blowers could coordinate where they would fire. They would fire in patterns that would make it obvious to the player how to avoid getting hit. We prototyped several patterns, but wound up using a line and a circle pattern while the player was on the ground. What's neat about having a pattern like this is that you can easily make the pattern bigger or smaller based on the number of enemies that are participating. This allows all the blowers to keep firing and makes the pattern more dangerous, yet doesn't affect the player's ability to parse what is going on. In order to prevent the player from feeling overwhelmed, we do space our barrages out by about a second. In between roughly every 2 to 4 barrages, we wait an extra long time of 4 to 5 seconds before we resume firing. When the player is grinding, we also add a special pattern. We walk the grind lines in exactly the same way that the player character is going to go with no stick input and fire our shots along there. This guarantees that if the player doesn't react, he's going to get hit. Additionally, all of this group targeting behavior gets shut off if the player chooses to rush an individual blower. At that point, that blower is free to fire directly at the player as much as he wants. Ranged enemies that fired straight-line projectiles, however, needed a different solution. Since they obviously couldn't draw out patterns on the ground, we started by looking at solutions from some of our past games. In Ratchet & Clank, for example, off-screen enemies will oftentimes try to deliberately miss. In Resistance, we would make guys who are off-screen fire their first volley in front of the camera and then shoot at the player with steadily increasing accuracy. We came up with some rules for nerfing an enemy's accuracy based on our experience from those games. The first was that on-screen enemies inside of their ideal range should always be accurate. The second was that enemies outside their ideal range should always be inaccurate. Off-screen enemies that are still inside their ideal range should miss with one volley and then try and become accurate. Off-screen enemies that are very close to the player should always be accurate. We added this rule because the majority of the time we found out that the player knew the enemy was there, and usually because they had deliberately turned their back on them for some other reason, and it felt really dumb to have the AI miss in this case. We added one final fifth rule, and that was one character should always be allowed to shoot accurately. So even if everyone is far away, at least one of them will be accurate, threatening, and engaging the player. All of this worked really great until the player started traversing again. Scabs use hit-scan bullets, and this means that the bullets will hit their target the frame they are fired. The previous rules kind of work okay when the player was on the ground because that forced the player to respond, and we trained the player so that he knew that he needed to get up on traversal. However, allowing them to be accurate while the player was on traversal, just because the scab was on screen, was way too punishing. What we wanted was for the scabs to kind of encourage the player to stay in motion. First, we decided that the scab should shoot the player if he used the same bouncy too many times in a row. I'm changing bouncies frequently and the enemies are unable to hit me. But here, as I stay on this same bouncy, they become accurate. As I start to change bouncies again, you'll see them lose their accuracy. And then when I come back around here, they regain it. The other case we needed to handle was what to do when the player is up on a grind. We wanted to discourage the player from just finding a tiny little grind loop or going back and forth in the same spot. What we did was track how much we think the player is moving via breadcrumbing. Here you can see the player moving around in a large circle. Here's that same circle from above. I've turned on our breadcrumbing debug, and we try and drop one of these spheres roughly every half second. We then track how long the player is in each sphere. If the player stays in any one sphere for too long, then he's considered not moving and we should shoot him. When we go to drop a new sphere, we delete the oldest one that the player is no longer in. If none exist, then we don't create a new sphere. Here's what it looks like from the player's perspective. I've turned off the debug display because it makes it impossible to see what's going on. But as I'm grinding forward, I don't stay in any of those spheres long enough to make the enemies become accurate. And this is fine because it encourages our core gameplay. But as I come back around here, I start grinding back and forth, and the timers start ticking up, and I'm going to start getting shot. It's also worth noting that we increase the speed that scabs become accurate over the course of the campaign. This applies both to the number of times that you can use the same bouncy and how much you need to move while on grinds. During their first encounters, scabs are very, very forgiving. Now, Physco shooters don't use hit-scan bullets. They fire slow-moving shots. And while our initial 5 rules on accuracy worked pretty well when the player was on the ground, the scab solutions didn't work at all when the player was traversing, because regardless of if they were trying to actually hit the player or deliberately miss, you'd still wind up with a completely unparsable hail of bullets. Instead, we decided that what they should do is use their bullets to create hazards in front of the player. If their target is going to be using a bouncy, they predict where they think that target is going to land and fire all of their shots there. The idea is to create a hazard that the player needs to respond to. If their target is on a grind, they trace ahead on the grind, similar to what the blowers do in the group targeter. They then fire all of their shots through a single position. Again, what we're trying to do is create a hazard that the player needs to respond to. Because all of the bullets go through a single spot in a straight line, it makes it much, much easier for the player to parse what is going on and what I need to do to avoid being hit. I want to mention one final problem that we always seem to run into with ranged enemies. In previous videos on Occlusion and Perches, you've seen enemies repositioning a lot. And this is fantastic when there's one guy, as it makes him feel aggressive and dynamic. But when you've got 3, 4, or 5 or 6, in our case, all constantly repositioning, then what you're really going to do is completely overwhelm the player. The player will stop being able to parse what is going on. Next, they'll lose awareness of where things are on the battlefield, and then things start to feel random and very quickly frustrating. It's not a really hard thing to do, but limiting the number of shooters in motion can have a big effect on how readable your combat is. And if you can bias this towards guys that are on screen, that's even better. Our enemies were already organized into squads for other reasons, and so we just piggybacked on top of that and said that enemies are allowed to switch markup if no other markup using enemy class in their squad is currently in motion, if they're being actively damaged, or if the player is too close to them. I'd like to take a brief moment now to talk about a few of the things that I've learned and a few of the things that I think we need to look at going forward. Sunset Overdrive is by far the most complicated game that we've ever made, and this talk has only touched on a small fraction of the systems that actually drive our AI behavior. And this makes testing both really important and really difficult. I should have had our QA team using some of the simple test levels that you've seen footage from to test our AI features. Instead, our QA team spent most of their time playing the shipping game in the shipping world. And it's very hard to notice when something like clue weighting, part of a layered system, breaks. Enemies continue to be able to chase the player. The game doesn't crash. There aren't asserts. Missions are still completable. But what happens is you get enemies queuing up at pieces of traversal, and things get a lot easier and a lot less fun. And well, during optimization, we did actually have some bugs creep in, and both our review build and the build that we sent out to streamers had completely busted clue weighting. I feel like a lot of the early coverage actually mentioned that the game looked a little bit too easy or a little bit too monotonous, and this was likely a huge part of that. Fortunately, we were able to get these issues fixed, but had I had someone loading up that test level with the fence once a week and testing it, this would never have happened. Something else I think that we need to start looking into doing is making our path queries a little bit more customizable. Most of our time spent on nav mesh and nav queries for this project was spent reworking and optimizing things to handle the dramatic increase in the size of our world. Right now, the queries themselves are fairly simple. You pass in 2 endpoints, a group of influence spheres, and get back a shortest path that takes into account any clue costing that's going on. Making it so that we can write custom path queries that don't necessarily return the shortest path, I think will have some great results. In particular, I'd like to experiment with path finding that understands arc angles, as well as using the nav mesh to help us discover nearby markup, perches, or occlusion. Speaking of markup, while we have prefabs similar to Unity for placing groups of assets, this didn't work very well for nav clues. The clues themselves need to actually be on the ground when the nav mesh generates in order for them to properly stitch in. And if we put them in a prefab, we don't know if that rail is on top of a building or at street level. And there wasn't time to change either our builders or the editor to make this happen automatically. So all of the nav clue markup that you've seen in this presentation and all of the markup in the world, which is about 100,000 clues, had to be either placed or adjusted by hand. And as you can imagine, this was a massive drain on our designers. And we need to look into ways to either procedurally generate this markup, validate and change markup that has been placed, or at least make tools to assist designers with placing this markup. I'd like to leave you with 3 last pieces of more general advice about creating enemies for an action game like Sunset Overdrive. These are things that I constantly came back to while trying to overcome many of the problems that you've seen me talk about in this presentation. You don't need to be doing advanced group tactics to benefit from thinking about things at a macro level. Don't shy away from little components, systems, whatever your engine supports to do some processing and keep some data about things at a group level. Even if what you're solving doesn't seem to be an intrinsically group problem, it's oftentimes incredibly useful to be able to ask questions or to think about combat as if it's a big singular thing. If a player can't parse what an enemy is doing, that enemy is not going to be fun to fight. In a test level, with one enemy, it should be immediately obvious what that enemy is doing, both through visual and audio cues, so that it is obvious both on screen and off. If it isn't, then once you get that enemy into the game with all the other enemies, the effects, the background, the sound, the player is going to be overwhelmed. This also means that they need to stand out from each other and the background. You need to pay close attention to silhouettes and where in the environment their behavior is going to put them. In Sunset Overdrive, we oftentimes partitioned our enemies. For example, our mugger classes stick to walls, blowers use perches, wingers are up in the sky, Herkers are much, much larger than everyone else, and then base OD are on the ground. The final and most important piece of advice that anyone ever gave me was to focus on testing player abilities. Don't just design your enemies to do something that looks cool. Figure out what kind of a response you're trying to elicit from the player. What role does this enemy play in your game? How do you want combat to play out versus that enemy? How are all of these things different from your other enemy classes? If you don't do this, then you run the risk of having combat that might be visually distinctive, but from a mechanics and gameplay point of view, it's likely going to be highly monotonous and not nearly as good as it should be. So with that, I'd like to thank the following people for helping me put this presentation together. And I'd also like to remind you to please leave me feedback later, and I'll take as questions for as long as there's time. Thank you.
So great talk. Question about all of the occlusion testing that was done per enemies. I imagine that was probably a pretty big bottleneck in performance. And first of all, was it? And second of all, did you use round robining or anything for addressing that because you have lots of hordes of enemies?
Did we use what?
Round robining? Like, do you do different checks on different frames?
There are kind of two parts to what was a drain on performance with occlusion. One is actually doing all the computation to compute the actual tangent positions and that. And the other problem is, the bigger problem was round robining all of the collision tests that we do at runtime to check, hey, can this piece of occlusion see to this target? So yes, we did use round robining, and towards the end of the project, we shifted all of the actual math for computing tangents onto a job that could run on another core.
Thank you.
You're welcome.
Great talk, thank you.
Thank you.
I was just wondering how you exposed some of those systems to the designers so that they could script or call specific points and behaviors when they needed to?
So the main way that our designers script our enemies is they have what's called a combat anchor, which is just a volume that they can place, and that heavily biases the enemy's either occlusion or perch selection to trying to get to that volume. So basically, and they can change what that volume is at runtime, and so whenever the enemy finishes their attack routine at this piece of occlusion, they'll say, oh, I need to be over there, so all of the pieces of markup that are more in that direction look way better, so I'm going to get up and move in that direction.
It's like a priority POI kind of thing?
Yeah. Except it's the big thing was that it's not we ran into a lot of problems with this in past games where we let designers grab a guy and say, you go here now. And so we wanted it to be more of a soft thing where it was kind of, I'm going to move where I want the battle is to over here, and as soon as it doesn't look awkward for the enemy to get up, he should reposition.
Thanks, that's awesome.
Cool.
I'll ask one. So you said, and I was going to ask before you mentioned it, that it's a lot of manual designer placement.
Unfortunately.
Did you guys try more procedural work and shelve it for a reason, or was it just never a reality in your production cycle?
Okay, so the question, which I've been forgetting to repeat, was did we try doing more procedural generation? We do some procedural generation for some parts of it. It basically came down to time. When we discovered that, hey, this was going to be a big problem, we were probably 6-7 months from shipping, and it was literally a question of, do we want to cut the Physco mech, one of the bosses, and have a programmer work on that? Or do we want to get some smart people from QA, teach them how to put these clues down, and then have them do it? It's unfortunate, and like, I wish that we had foreseen it coming, but we did the best with what we could.
Gotcha.
All right, thank you. I'll be in the wrap-up room for a bit if you have questions that you'd prefer to ask in person. But thank you.